Welcome back. In this video, I will discuss the theory behind capillary jet breakup and the experimental setup for characterizing jet length, drop radius or size, and breakup wavelength. Capillary jets can be formed when liquid emerges from a small diameter circular orifice into an immiscible fluid at sufficient velocity. Atto observed that the liquid cylinder becomes unstable when its length exceeds its circumference. He modeled the jet with an axisymmetric and sinusoidal disturbance, where we can see here we have an axis that is the axis of symmetry, which we usually denote by z if we're in a cylindrical coordinate. And the disturbance is sinusoidal, where we have sinusoidal wavelength disturbance. We can further characterize this by looking at the distance between the orifice and the final drop that is part of the jet as the length L. And we can also look at the radius of the orifice as A, and the wavelength of the sinusoidal disturbance can be denoted lambda. And we can see that when the length of the cylinder exceeds its circumference, we see a jet breakup. So instead of having a jet that is continuous, it breaks up into droplets. These droplets will have lower surface area, therefore minimizing surface free energy, and the process of breaking up capillary jets is therefore spontaneous. If we have a laminar flow, then the jet velocity will impact the jet length, and we can look at this in the graph that we have plotted the jet length on the y-axis and the jet velocity on the x-axis to see how jet velocity impacts the jet length. In the beginning, we will have a dripping region where we have a flow rate, so there is no jet formation. This is a dripping. This is expected because if we have a laminar flow through an orifice, then if you have a very low jet velocity or volumetric flow rate, then there will be no jet formation and it just drips off. To increase the jet velocity, we will go into the Rayleigh region, where the jet length is linearly proportional to the jet velocity, and there will be laminar jet formation. Before going into the orifice, the liquid is laminar, and going out of the orifice, there will be sinusoidal disturbances. However, the flow is still laminar. And then there will be regular jet breakup with uniform drops, sizes, and spacing, even though it might have some satellite drops in between. After the maximum jet length, so here we have a maximum jet length L, there will be irregular jet breakup and spacing, so the spacing might be ununiform and the breakup sometimes might break, sometimes break. And in a higher jet velocity, there will be atomization, where the laminar liquid coming out of the orifice just produces a spray of droplets instead of having a discernible jet or breakup. It's just all droplets, so it will be hard to define the jet length in that case. In general, we can define a surface disturbance amplitude eta that is equal to eta naught, which is the initial disturbance, multiplied by e to the beta t, where beta is the growth rate and t is the time, multiplied by cosine k times z, where k is the wave number and k is equal to 2 pi divided by lambda, which is the wavelength of the jet. And z is the coordinate, that is the axis that is axisymmetric. Graphically, the surface disturbance amplitude can be visualized by graph. We have a sinusoidal disturbance initially, then the initial disturbance is eta naught, and the disturbance at any time will be eta. Get the jet length, we will assume that when the surface disturbance amplitude is equal to the jet radius a, then the jet will break. So if we write it out again, we have eta equals to eta naught e to the beta t cosine k of z. So we're assuming when eta is equal to jet radius a, then it will break up. So at that breakup, we have a maximum growth rate, which is beta star I define here, multiplied by the time, and the cosine k of z, this disturbance term become. And to solve for t, we have a divided by eta naught, take the natural log of both sides, and then I will divide the beta star term left, and I'll solve for t. And notice that t is just equal to the distance divided by velocity u, use the jet velocity. So if we can rearrange, arrive at L, the jet length is equal to the velocity u divided by the maximum growth rate multiplied by the natural log of radius divided by disturbance. At that breakup length, we can also define the maximum wavelength as the lambda star. We can use that to calculate the drop size, which is the volume is equal to pi times the radius square multiplied by that disturbance wavelength. Now Rayleigh made some simplifying assumptions on these general forms of analysis by assuming axis symmetric disturbances. We have inviscid or zero viscosity liquid jet coming from the orifice, and we also have inviscid zero density medium. For example, in our case, the liquid jet might be water and the zero density medium air, and there will be no gravitation in the analysis. Rayleigh's analysis suggests that the wavelength number that maximizes beta, which gives beta star, is k star roughly equal to 0.697 divided by the jet radius a. And we can then calculate the wavelength that maximizes beta using lambda equals to 2 pi k, and multiply that, we have 9.02. We then calculated the maximum growth rate, and in that case it is the square root of 0.12 multiplied by the surface tension, denoted by sigma, multiplied by the density, divided by the density multiplied by the jet radius. If we use the general jet length equation here and plug in the beta star into it, we can get the jet length determined by Rayleigh's analysis. And we can use this to experimentally verify Rayleigh's analysis validity. And finally, if we substitute the wave number that maximizes beta into the drop size equation, we can get the drop size from the Rayleigh's analysis using his simplifying assumption. To improve Rayleigh's analysis, Weber did some analysis by relaxing the assumptions from the Rayleigh's analysis. We now know the non-dimensionalized number as the Weber's number to determine whether we should use the Rayleigh analysis or the Weber analysis. The Weber number is defined as the jet velocity multiplied by the density of the external medium. Rho of E is density external medium. For example, in our case, we're using air. U is the velocity and A is radius divided by the surface tension. If the Weber number is smaller or equal to 0.1, we use the Rayleigh analysis, simpler one. But if the Weber number is greater than 0.1, we use the Weber analysis that we will detail. And the Weber's number can be interpreted as the drag force divided by the surface tension. So that we use Rayleigh analysis when Weber number is lower than 0.1, that is, when drag force is negligible compared to the surface tension. However, if the Weber number is greater than 0.1, where the drag force is significant when compared to the surface tension force, we will use the Weber analysis. The Weber analysis relaxes the assumptions by using finite jet liquid viscosity and finite density for the medium, and it also assumes an asymmetrical disturbance instead of axisymmetrical one. Weber defined a set of maximum growth constant using this term, and then calculated the wave number that maximizes the beta to get beta star using k star. And substituting these into the general form, we can derive the Weber analysis wavelength and substitute the wavelength into the jet length and the drop size that can be predicted by experiments. We can perform experiments to verify the validity of Rayleigh's analysis and Weber's analysis based on their assumptions. The experimental setup has a constant head tank that fills the liquid of interest, and in this case we're interested in water and the silicone oil. So they will have different densities and surface tension. Those liquid properties will affect the analysis that we do. The tank is connected by a tube down, so that at here we have a nozzle that is horizontal but slightly tilted up, so that when the jet is breaking up around here, the height is the same as. So if we zoom in at the nozzle, we will see that the nozzle is actually slightly tilted upward compared to the horizontals, so that when we have jet going on and it breaks apart, the height is roughly the same. And of course, the angle here drawn is exaggerated. It's not that big. When we perform the experiment, we will use a camera to capture the jet breakup. And from those images, we can use image J analysis to determine the jet length and the drop radius, and therefore the drop size or volume, assuming they're spherical. And also determine the jet breakup wavelength as well as the undisturbed jet radius. And note that the nozzle will have 3 sizes of nozzle, which effectively corresponds to different undisturbed jet radius. We'll also determine the effect of volumetric flow rate on jet breakup. Volumetric flow rate can be changed by moving the nozzle height up and down. So if we have a higher height, then the changing height is lower compared if we have a lower height. So if we have a lesser changing height, then we'll have lower volumetric flow rate. If we have a higher changing height, then we have a higher volumetric flow rate. And you can determine the volumetric flow rate using a bucket stopwatch method, where the volumetric flow rate is the volume of water collected by a bucket in a set time interval. And assuming we know the density of water, we can calculate the volume from the mass of the water. The volume can be calculated by m mass, can measure divided by the density. we can get the volumetric flow rate. So in the experiment, you will test 2 different liquids at 3 nozzle sizes at different flow rates. And from those conditions, I will want a graph of the jet length with respect to the jet velocity, so that we can see if we have different regions that we have seen earlier. So initial region, the Rayleigh region, that is quite linear, and the maximum. To determine if we're actually in the Rayleigh region, where the jet length varies linearly with the jet velocity, we can plot the jet length with respect to all these terms, because this term is a constant and this term is also a constant. We're only varying u, so we can plot on the x-axis u multiplied by rho e to the third sigma to the 1, so that we are expecting a linear. And this linear graph would be corresponding to the above figure as the Rayleigh region. And the slope of this graph would be equal to 8.33 times the log of a divided by eta naught. And we already know a, so we can solve for eta naught, the initial disturbance. Because we know the a, we can also calculate the theoretical drop size determined by Rayleigh and compare it with the drop size that we determined from image analysis. Compare theoretical and actual drop size. In this video, we discuss the capillary jet formation. How the jet length depends on the jet velocity or laminar flow. We looked at how Rayleigh's analysis can help us predict jet length and drop sizes, and the Weber's analysis relaxes some of the assumptions made by Rayleigh. Finally, we'll look at how to set up an experiment to characterize the capillary jet breakup by looking at jet length, drop size, breakup wavelength using image analysis.